Welcome to the captivating realm of deep learning. Ever wondered how computers can recognize images, understand speech, and predict outcomes with astonishing accuracy? It's all thanks to the remarkable capacity of deep learning to mirror the intricate workings of our brains. No need for complex math here, just your curiosity and an open mind. Picture this, a world where machines think and learn like humans. Let's delve into this fascinating journey together. What is deep learning? Deep learning, a potent AI branch, trains computers through experience. Just as you recognize cats from seeing many, these models learn patterns from data. They drive technology advancements, fueling voice assistants, self-driving cars, and medical diagnosis tools. The deep aspect denotes the layers of learning within. In a world transformed by these models, understanding deep learning is essential for grasping the future of technology. Imagine your brain as a vast network of billions of neurons, intricately connected to help you think, learn, and remember. Deep learning models draw inspiration from this complex biological system. In the biological realm, neurons receive, process, and transmit signals. Conversely, artificial neurons handle numerical inputs, perform computations, and generate output data. Both systems learn by adjusting connection strengths over time. This symbiotic relationship between biological and artificial neurons forms the foundation of deep learning. Just as our brains adapt and grow, these models evolve through learning. Imagine a neural network as a well-oiled machine, with different layers acting as specialized teams working in harmony. The input layer, with its 4 nodes, receives raw data, such as pixel values from an image. Next, the hidden layer, with 6 nodes, diligently processes and transforms the data, extracting key features. Finally, the output layer, consisting of 3 nodes, delivers the ultimate prediction or classification. Each layer plays a crucial role in unraveling increasingly complex patterns, much like a symphony building towards a crescendo. And just like that, neural networks decode intricate data, layer by layer, to unveil insightful predictions. Ever wonder what neurons actually do? Picture them as tiny decision makers in our artificial intelligence, processing incoming information with finesse. First, they receive inputs from previous neurons. Then, they multiply each input by a specific weight, reflecting its importance. Next, they sum up all these weighted inputs before passing them through an activation function to produce an output. During training, the network fine-tunes these weights, determining which inputs hold the most significance. Neurons, in their simplicity, hold the key to complex decision-making in AI. Activation functions are the secret sauce that supercharges neural networks. Think of them as the decision makers. They inject nonlinearity into the system, enabling networks to decipher intricate patterns beyond mere straight lines. The sigmoid function squeezes values between 0 and 1, making it ideal for handling probabilities. Meanwhile, ReLU is the minimalist hero, setting negative inputs to 0 and retaining positive values, a straightforward yet potent approach. On the other hand, TAN, akin to sigmoid but ranging from -1 to 1 and centered at 0, provides a balanced perspective. These functions are pivotal in steering neural networks towards understanding complex data structures. Ever wondered how neural networks actually learn? Well, it's all about training. Picture this, the network makes predictions, evaluates its mistakes, and fine-tunes itself for better accuracy. This iterative process repeats tirelessly until perfection is achieved. The secret sauce? Backpropagation. This genius algorithm precisely adjusts each weight in the network to minimize errors. It's like a self-correcting puzzle, piecing itself together with every mistake. And voila, that's how neural networks master their tasks. The journey from prediction to precision, all thanks to the magic of backpropagation. In the intricate dance of the learning cycle, data takes a journey through the neural network, paving the way for predictions. As errors are meticulously calculated, a critical moment emerges, the comparison of prediction and truth, shaping the network's path forward. Through the backward pass, errors flow in reverse, guided by the intricate backpropagation process. The network evolves as weights are adjusted, honing its predictions and reducing future inaccuracies. This iterative cycle unfolds, each repetition refining the network's understanding of the underlying data patterns. In this dynamic dance of data and computation, the neural network learns, adapts, and grows, unlocking the secrets hidden within the data. Picture yourself navigating through dense fog on a hiking trail, aiming to reach the valley's lowest point, akin to minimizing errors in a neural network. Just like sensing the downhill direction while hiking, backpropagation calculates gradients to guide weight adjustments. It's all about taking incremental steps towards better weight values, much like descending the steepest path until you hit the valley floor. This technique, known as gradient descent, steadily fine-tunes the network for optimal performance. Keep adjusting, keep improving. Diving into the mechanics of backpropagation reveals a complex web of calculations, rooted in the simple question, how do weights impact error? By applying the chain rule, we trace this influence back through the layers, pinpointing the role of each weight. Gradients then guide us, indicating the necessary adjustments to minimize error. Through meticulous weight updates, the network fine-tunes itself, inching towards optimized performance. Remember, the learning rate dictates the size of each adjustment, striking the right balance is paramount. Overshoot or stagnation looms with misjudged rates. In grasping this delicate interplay, we unlock the key to efficient learning. In the world of deep learning, the power of neural networks comes with a challenge: overfitting. These models excel at memorizing training data but struggle to adapt to new situations, much like a student who can regurgitate answers without grasping the core concepts. Just as the student falters when faced with slightly altered exam questions, neural networks can falter when presented with new data. To combat overfitting, we must delve deeper into understanding the nuances of model training and generalization. Let's explore how to harness the strength of deep learning while mitigating the risks of overfitting. Ever wondered why your model performs perfectly on training data but poorly on new data? It's the battle between overfitting and generalization. Overfitting occurs when your model learns noise and random fluctuations in training data, fitting every detail, even errors. On the other hand, good generalization happens when your model learns the true underlying patterns, leading to good performance on both training and test data. Remember, a simpler model that captures essential relationships often outshines a complex one. So, strive for generalization to achieve reliable predictions across the board. How can you tell if your model is overfitting? Keep a close eye on key indicators during training: the epoch, training error, and validation error. As training progresses, watch for a divergence where the training error continues to decrease, but the validation error starts increasing post-epoch 10. This divergence signals overfitting, where the model memorizes the training data instead of learning generalizable patterns. In essence, the telltale sign of overfitting is this: while the training error decreases, the validation error increases, indicating a lack of generalization beyond the training set. This phenomenon highlights the importance of monitoring model performance to ensure robustness and reliability in real-world applications. Remember, detecting overfitting early allows for adjustments to be made, leading to more accurate and reliable models. Regularization, keeping models honest. How do we rein in the wild learning of neural networks? Regularization techniques act as guardrails, guiding models away from overfitting while still allowing for effective learning. By promoting simpler, more robust solutions, these techniques pave the way for better generalization to new data. Rather than stifling the model's potential, they refine its focus. Think of regularization as the steady hand that shapes a model's growth, ensuring it stays on the path of reliable, adaptive learning. Regularization techniques are essential for training robust neural networks. L1 and L2 regularization add penalties based on weight magnitudes, promoting small weights, L2, or sparsity, L1. Dropout randomly deactivates neurons, fostering diverse representations and preventing codependency. Early stopping monitors validation error to prevent overfitting, while data augmentation enhances training sets through modified examples. By leveraging these techniques, models can achieve better generalization and performance. Ever wondered how dropout enhances neural network resilience? In each training cycle, dropout shakes things up by randomly deactivating neurons. This forces the remaining neurons to become adaptable, making predictions without relying on a specific subset. At test time, all neurons are back in action, but their outputs are adjusted based on the dropout rate used during training. The outcome? A robust network that doesn't lean too heavily on any single neuron or connection. Think of dropout as the network's personal trainer, pushing it to be strong and versatile. So, embrace dropout for a network that thrives on flexibility and resilience. When faced with the challenge of choosing the right regularization technique, tailor your approach to suit the specific characteristics of your dataset. For small datasets, opt for strong regularization methods such as high dropout and robust L2 regularization, alongside aggressive data augmentation and early stopping. Simplifying the model architecture can also be beneficial in this scenario. Conversely, when dealing with large datasets, moderate regularization suffices, allowing for the utilization of deeper and more complex models with less risk of overfitting. Focus on refining the model's architecture and optimization strategies. For complex models, employ a combination of various regularization techniques, closely monitoring validation metrics, implementing batch normalization for stability, and incorporating learning rate scheduling. Remember, the key lies in adapting your regularization strategy to the unique demands of your dataset. Balancing the many factors in building a successful deep learning model is key. Remember, it's an iterative process, you won't nail it on the first go. Experiment with different setups and be ready to tweak. Data prep, model design, training, validation, and deployment form the core steps. Keep an eye on validation metrics and adjust your approach as needed. Deep learning thrives on iteration and adaptation. As we wrap up, let's recap the key insights from our dive into neural networks. Picture this: neural networks are like a series of interconnected layers, each layer transforming and extracting data to unravel complex features. Through backpropagation, these networks learn by adjusting weights to minimize errors, paving the way for progress. However, beware of overfitting, a trap where models memorize data instead of grasping broader patterns. To strike a balance, techniques like dropout and weight decay come into play, ensuring models generalize well to new data. Remember, in the world of neural networks, balance is key. Welcome to the final slide, where we put your newfound knowledge to the test. Let's dive in with a quick knowledge check. Can you name the 3 main types of layers in a neural network? Input layer, hidden layers, and output layer. Next, in simple terms, what does backpropagation calculate? It determines how much each weight contributed to the error, guiding the network's adjustments. How about spotting overfitting? Watch for the training error decreasing while the validation error rises. Lastly, name 2 regularization techniques and their functions. Dropout randomly deactivates neurons, while L2 regularization penalizes large weights. Remember, in the world of deep learning, the journey only grows more exciting. Keep exploring, experimenting, and honing your skills. Congratulations on mastering the fundamentals.